Greetings, this is Artie from Artifact Electronics. Today we have yet another thrift store find. This is a Leader LDC-822 digital counter rated at up to 80 megahertz. And this one cost $5. I plugged it in at the store and it lit up, but I couldn't really test it. At least it looked like the display was good, or the displays. But at this price, I figured at about 55 cents per display digit, why not? Let's see what it can do. So let's see what she looks like. It's got a nice vacuum fluorescent display. So it obviously came up in, let's see, it's pressed down in the period measurement mode where it needs a trigger input to start and end. Well, let's switch to frequency counting. Again, with no input. Let's put some more digits on the screen. So it's, well, the display's beautiful actually, but let's see if it actually works. Well, we need some frequency from the function generator, and for that we're going to use yet again the super accurate Heathkit counter. Now, one other thing I noticed immediately was, see how the gate is blinking, showing you the update rate? This also has a gate light, but it doesn't seem to be doing anything. Oh, did you see that? It just lit up. Let's put it in 1 second. Well, now it won't come on anymore, but we'll see. So the frequency, let's see what the function generator is outputting. So it says 80 kilohertz. Let's see if we can get this to 100. That's pretty close. Wow, a little more. Yeah, remember I did clean the pots on the chrome height, but looks like I didn't do a good enough job, because the minute I touch the dial it changes, but when I let go. Alright, we'll just call it 100K. Well, okay, fine, 98K. And let's go to a lower update rate. So it's kind of all over the place. Oh, the light came on again, which is being, which you can't see. There you go. See it flickers right now in 1 second intervals. Really quickly, and then of course we can go to 10 seconds. You know what, let's put a T on this and have a look, compare them side by side as far as the frequency counting is concerned. Well, it looks like things are pretty close. Oh, no they're not, because I got this on 10 seconds. No, they are. They're almost identical. They're very, very close, and this light's working now, the gate light, but well, that's pretty impressive then. Let's go to a kilohertz setting on this and on this. So it looks like that, I mean, if they're both lying, they're very well coordinated, but it looks like this thing's working now, but we just lost, well, no, we didn't lose. Yes, we did lose the gate light. There's something loose in here. So let's go inside and find what could probably be causing the gate light to not function all the time. And let's go back to 100K here. Ooh. Beginning to deviate over here. Oh, come on, things work so nicely. And now it's degrading when it's heating up. Trying to come back, but no, it's kind of all over the place here. They have the same gate timing. Well, almost the same. Oh, let's have a look and see. So the first concrete problem I'm going to go after is the intermittent nature of the gate light. Because the frequency, I mean, now that I'm looking at it, the frequencies are in sync again. So, but there's definitely something intermittent going on here. But the gate signal it's easier to replicate, I would say. So let's have a look at that and see if that gives us any clue as to what else is happening. We obviously know that the gate is working because we can see the display update. Now from the schematics, this line over here represents the interface to the display module, and we see the gate signal, that the gate light is being driven through this signal. And if we trace it back, it's actually coming up here as a pull-up and gets fed by the Q bar output of this JK flip-flop over here. And that's probably why the gate's working, is because the Q output is generating the gate signal, and I guess they're just using the Q bar to generate the light, but something here seems to be wrong, because sometimes the light works and sometimes it doesn't. Now banging on it seems to make it work, so we may have some solder joint problems somewhere on this chain here, and we should definitely have a look inside now. So I opened her up, and the Heathkit is showing 95 kilohertz, and this one's showing 66. Just jumped to 68, and the gate light is not working. So what I did was I went inside and actually found where the gate light connection is. Let's see how close we can get here. So the gate light connection is actually Hello, where'd you go? It's right here. This is the pull-up resistor. And let's see if I can get something that is recognizable on video here. Because I may have found... Well, it's hard to see from here, but you're going to have to take my word for half of what I'm just saying. But what I noticed is the resistor here, I mean, it's a two-sided board, but most of the action is on the bottom side of the board, and I guess the through holes don't have vias, so it is extremely important that the components get soldered both on top and on the bottom to provide the connectivity from any traces on the bottom to the top. And it's kind of hard to see, but even though this is soldered over here, the pin of the IC, the pad for the pin, there's no solder on it, and the pin is kind of floating freely in there. Well, it's not floating, it's, you know, friction. It is being kept in place by friction, but there is no solder on the IC pin itself. And looking through this board, that seems to be a common malady of wherever there's a, let's call it, you know, a pseudo-via that connects on top of the board. And I guess when they wave soldered this, they got the solder to stick to the pins coming through from the bottom, like here. But the solder didn't really flow onto the IC pad or whatever it was connecting to. So what I need to do is get this board out and basically look at every single connection on top and see if there's any place where there's an insufficient solder flow and touch that up. Let me see if I can show you by sticking the pin in there that I can make the gate light work by simply pressing. Well, it's not going to work. It's not going to work with a plastic pointer. So let's get something conductive. Make sure the gate light's in here. And I'll just make a connection with the screwdriver. And now, of course, see, it stays on. Oh, I shorted something else here. But yeah, by pressing against that connection, I make it come and go. So I'll need to take out the board and start touching up all sorts of solder connections there, and see what that does for us. If that takes care of that horrendous frequency inaccuracy we were seeing when it's counting. So taking it all apart, trying to show you a better view of it. Of course, my camera won't go in close enough to properly focus on this. Let's see. And a miserable fail. So let's see. Well, this is just going to have to do. This is the affected connection. This is where the pull-up resistor connects to both top and bottom of the board. And then you can kind of see that the pin pad itself over here is totally devoid of solder. I mean, the pin is just sticking in there. I don't know whether they didn't flux it properly during wave soldering or whatever, but there are a couple of spots on the board that look like that. So maybe that'll give you a better idea, and I'll just have to go through and see if I can create some good solder joints for every place on the board where that happens, and see what that changes, if anything. So I have good news and I have bad news. The good news is that I went through and resoldered everything, that looked suspicious, and it fixed the gate light. But then when I turned it on, I still saw a large discrepancy in the frequency between the Heath and this guy. So obviously there's something else going on. But first, desoldering the actual pin pads was interesting because the pads as they were, this one in particular, point at it, was really stubborn. The pin pad would not take solder. So what I did was I used a bit of flux, basically applying it with a toothpick, and then we got a good connection. And this is, of course, I couldn't get a picture of it before because the camera was refusing to focus. And as you can see now, it focuses. That's because I fooled it. I put a magnifying glass over it. But you would have seen that this connection, basically, there was no solder on the pin pad, and I couldn't get any on there. It connects to this through-hole connection here. But after using the flux, finally it flowed. And when I turned it on, the frequencies looked bad. So we still got the major fault to find, but some of you looking at this may see what I'm thinking about now, and that is the enemy of the electronics people. And what that is an old, moldy tantalum cap right here. And there's actually another one over here. I measured them for shorts, measured them in circuit, got weird values, but that's because I got sidetracked and didn't deal with it. But my current suspect is this. So let's see if we can prove that theory. I pulled the evil tantalums, tested them. They tested just fine, both of them. I replaced them anyway, and that didn't fix the problem. What you're looking at now is while I was replacing one of the tantalum caps, I saw that there was another pin pad hidden behind a cap, another cap there, that also wasn't soldered. So I applied some flux, reheated it, made the solder flow, and here's the result. It is, well, at least it is tracking the value. I mean, the function generator is outputting about, the dial does say about 100 kilohertz, but they are tracking each other very well, which means that the clock in here is also running correctly. And I'm not going to mess with it because it's already showing that it's good. But I would say that it's fixed. One thing I should point out at this point is some of you may be wondering and saying, why didn't you just throw a scope at this thing and test all the signals and stuff? And the reason for that is that once I found the first problem, which I found visually, and determined that the problem was the factory soldering on this left something to be desired, I decided to continue my search in a visual sense because I really believed that the problem was what I showed you before, that some of the pin pads didn't receive enough, if any, solder, and some of them created some really intermittent connections, so that's why weird stuff was happening here. I think I found the last one, so I'm going to let it sit for a while and then put it back together, and then we'll make sure that when it's back together it still works. But looks like we're finally done with this guy. Alright, it's all back together. No leftover screws or brackets or anything like that. And seems to be tracking the frequency well. Should just compare the two. It's an approximate 100 kHz input, and it's showing that. We then have, well, we can go down to 1K, and there is 1K. And finally, what is this? 10 hertz. So it's catching all of those. And going back to the higher frequency, let's see if they track each other. So we're going to what? 284, it says. Well, it looks like they're on. I mean, that they compare pretty well. So they are, so whatever is coming out of the function generator is being detected equally by both of these. Finally, it will measure the pulse period, even though that's limited to like 10 hertz to 10 kilohertz. So let's give this guy's .500 hertz, which is right in the middle of its range for pulse pulse duration measurement. And that basically tells us that at 500 hertz we have a period of 2 milliseconds, which it is correctly showing. Now let's see what this guy says. Well, he does a little dance, but yeah, so that's working too. And if we go really low to 5 hertz, well, let's first see if we'll measure the frequency that low. Yeah, it will. And the period at 5 hertz is well, it doesn't look like you can measure that. Oh, there you go. It says 134 milliseconds. So I guess neither of these will properly measure the period, which is supposed to be 200 milliseconds. This one's kind of close. This one isn't. Well, yes, actually it is. The numbers match. I misread the decimal point. So they're getting pretty close to actually measure the period all the way down to 5 hertz. It's really useful, but there you have it. I hope you liked the approach I took this time. Instead of just sticking a scope, just doing mostly visual checks and stuff like that. What I didn't show was I did measure the power supplies right off the bat, and I must have deleted that footage, but it has plus minus 5 volts and 40 volts that goes to the VFD display, and the voltages were all present and within a few % of their stated values. So once I saw that, then I started digging. We looked at the schematic, and that basically gave me a starting point of where to visually inspect the board. And then of course we found the gate problem, and after that I figured that all of the problems that this displayed were caused by bad soldering practice when in the factory. And my guess is, I'm no expert in that, but I don't think the top of the board was fluxed correctly, and thus those pads just didn't take any solder. But it's fixed, and it won't be going to the landfill. Thanks for watching. Hope you enjoyed it, and support the channel. Make sure to subscribe, and we'll see you next time around.